Why will it
Hello, I'm Ron Thornton. I teach science, and I was just using a motion detector to plot my position versus time. As you can see from the graph here, I started out a little less than a meter from the detector. I moved away to almost 3 meters. I came back again to almost a meter, and then I started to move away. We found that this apparatus is a very effective way to teach students both motion and graphing. In the next few minutes, I'm going to show you how this motion detector, developed at the Technical Education Research Centers, or more commonly known as TERC, can be used with students. Let me first tell you how the motion detector works. The motion detector has a sonic transducer on the front that you may have seen on a Polaroid camera. It was developed by Polaroid, and it puts out a high-pitched sound. The motion detector works very much the way a bat navigates. The bat sends out high-frequency sound and waits to listen for the echo. By the amount of time that passes until it hears the echo, it knows how far away the object is that's reflecting the sound. The motion detector also works in this manner. It sends out high-frequency sound. When this sound hits something, an echo comes back to the detector, and the detector then acts as a microphone and detects that sound. The computer is able to calculate very accurately how long it took for the sound to come out and come back. By knowing the speed of sound, we can then plot on the screen how far away the object is. By taking the rate of change of the position, we can plot the velocity. Of change of the velocity, we can plot the acceleration. The motion detector is connected through the computer through a black box, a black interface box developed by Stephen Banish of TERC. The interface box is connected to the computer through the 16-pin game paddle port. The 16-pin game paddle port is inside of the computer. Let me show you that. Before removing or plugging anything into the game paddle port, turn off the computer. Inside the Apple, you can see the cable going to the game paddle port. If I disconnect this cable, you can now see the 16-pin game paddle port. I can plug this in, like so, and now the interface box is ready to go. The motion detector is plugged into the interface box using a standard telephone connector. And if I plug it in here into the first telephone connector next to the cable. Now, the software to run this comes on 2 disks. One program disk goes into drive 1, and if you have 2 drives, you can put the data disk into drive 2 right away, or if you have only 1 drive, it'll ask you to insert the data disk at the appropriate time in drive 1. If I now turn on the computer, the software will begin to load in. Sometimes we say the software will begin to boot. The program is loading. Pressing Control-T will put you into a special teacher's menu that has options useful for setting up for the class. main menu appears, you can move the highlight around by pressing the space bar or the arrow keys. When you've highlighted the operation that you want, in this case I'd like to go to Motion Grapher, I then just press Return. Motion Grapher appears, and I'd like to collect data. And here I am ready to collect data just as I did before. If I press Return, the motion detector starts, can pick up my motion, and I've made another distance time graph. Now, after I've made the graph, I could take a look at some other aspect of my motion, such as my velocity, which you can see here. Every place that I've turned around, the velocity goes to 0. Or, if I chose, I could compare, to make this point more obvious, I could show distance and velocity, or any combination of screens at the same time. And there you see, every time I turn around, the velocity goes to 0. Now, I also could have started by collecting, for instance, velocity first. To do this, I select velocity, and now, when I move, it'll measure my velocity. If I stand still, my velocity is 0. If I come forward, velocity goes negative. And there you can see a velocity graph. If afterwards I wish to look at the distance graph, I can do so. There's another way I can make use of the motion detector. If I escape back to the main menu, I can go to Motion Experiments and select a motion experiment that I've previously made. In this case, distance graph. When I load in distance graph, a graph will appear which you can see on the screen as part of data B, and the data that I ordinarily collect appears in something called data A. So I can use data A to put a graph over the top of this graph. The student's challenge is to imitate this graph by moving appropriately. If I try to do this, the first time I may not be nearly so successful because I don't know exactly what to do. Let me see what happens. Well, I'm off to sort of a bad start. If I move away now to make this, didn't quite stop in time. Now if I move away again, I've gone too fast. And overall, I didn't do too good a job. But if I try again with the practice that I now have, now I can move away. I have an idea of how fast I have to move. I went too far. So the second time is somewhat better, although to get it exactly right, I'd probably have to do it again. At any time, data can be saved to disk or read back from the disk. Let me show you how to read it back from the disk. If we escape to the Options menu, I select Disk, and I'd like to load the data into data A. After I select that, I'm shown a list of available data. There are 3 listed here: girls graph, tape, and back and forth. I select back and forth, press return, and it loads back and forth into the computer where we can see it. Now, I can either look at it here, change the scales to make it better. For instance, if I'm unhappy with this scale, I can make it bigger by going to axes and changing the distance axes from 2 meters, from 4 meters to, say, 2 meters, and it replots it. Now, if I'm happy with this result, I may want to have a permanent copy so I can print it out to the printer. It's not always necessary to use the motion detector with human bodies. You can also use it to measure the motion of all sorts of objects. For instance, I've set up a ramp here with a 6-foot board and some books, and I have a cylindrical weight that I would like to see what happens when I roll it down the ramp. I've aimed the motion detector down the ramp, and if I set the weight here and start the motion detector, I can see what the motion of the weight's like. Here I was holding it still. It began slowly, it went more and more quickly. You can see the distance increasing much more quickly until it hit a pile of books to stop the weight at the bottom. I can take a look at the velocity graph also to see what this looks like. And here I see the velocity increasing, a straight line, until the weight hits the books at the bottom. Here's the distance on the bottom, here's the velocity graph. Sometimes it's nice to use an object that has substantial friction. If I take this toy car and roll it up the ramp and let it come back while the motion detector plots its motion, there are some very interesting things we can see about the graph. If we look at the graph, we see the sort of shape that we saw before with the cylindrical weight, for instance right here, and we see another such shape right here. But they're obviously different. What is the difference? Well, watching the car, it seemed to me that the car, when it was coming back down the ramp, was speeding up much slower than it was slowing down when it was going up the ramp. If we look at the velocity graph, you can see where I pushed the car right here. When I let go of it, the car began to slow down very rapidly until it turned around. Here's the point where it turned around. Then, after it turned around, it didn't speed up nearly as rapidly as it slowed down. Now, the rate of change of velocity is related to the force. It must mean that the total force on the car is different when the car is going up the ramp and when it's going down the ramp. When it's going up the ramp, gravity is pulling it back, and the friction of its wheels is pulling it back. Those two forces are acting in concert to slow the car down. When it turns around, however, gravity is pulling the car down, and the force on the wheel is trying to stop the car from going down. Consequently, the net force is much less in the case when it is going up. And we see this difference right here. There are some sophisticated motions that can be analyzed with the motion detector. For younger kids, just seeing the phenomenon may be interesting. For older kids, older students, it's possible that they can do a full analysis of the motion using the graphs that are produced by the motion detector. If I place the motion detector on the floor below a weight and spring, I can plot something on the screen called simple harmonic oscillation. Now the motion detector is watching the weight go up and down. If I start the computer, we see the sinusoidal motion that's characteristic of simple harmonic oscillation. There are many more interesting things to show you than I can demonstrate in this short tape. But I hope that you've already seen that the motion unit is easy to use and very flexible. Students can take data quite easily and present it in a form that they can understand. After they take the data, they can change the scales to look at features they may have missed. They can store it to a disk and bring it back. They can print out hard copies that they can take with them for study. It's possible to compare a number of graphs at the same time to see how they differ. All these things are possible using the motion unit. If the teachers and the students set up a flexible laboratory, the students will be able to go after questions on their own. One of the most important ways to use this unit is let the students ask and then answer their own what-if questions. What if I do this? What if I hop like a bunny? What does that look like? What if I run quickly, turn around, come back? What happens? If I have a number of students in a row and one of us hops out, what does the motion detector see? All these various sorts of questions can be answered by students and by teachers. The materials that I've been showing you today are available from HRM Software in New York. A manual of student experiments and a teacher's guide to go with it to help you to get the most from this powerful instrument. Teachers from middle school through college have used the motion detector and found it an exciting way to teach their students science. I hope that you too will find the motion detector enhances your teaching and encourages your students to investigate the physical world around them.